Okay, here we go with a video that's just going to talk about some of the basics about work and energy, what it is we're trying to do in this unit in general, and some of the equations we're going to be using. The basic idea is we can solve problems in a few ways in physics. One of them is talking about forces, which we have a lot of experience with, and another one is by using work and energy. And we'll find that some of the problems are much easier to solve using work and energy. For example, if we're talking about things that are speeding up or slowing down, it's easier to look at things in terms of work and energy. Or if we're applying forces to things to speed them up and slow them down, work and energy is the way to go. I'm going to pull up the AP equation sheet here just to show you where we're looking at here. And it seems pretty daunting. We haven't looked at this in a while, but I want to show you some of the formulas we're going to be working with, so to speak. So here we have our formula for work. It looks a little bit different than what we've seen, and I'm going to show you what we get to here. This one's kinetic energy. This one is power as a rate, so we'll show you something as well. This is another one for power. This one is going to be gravitational potential energy, which we abbreviate as U. And then over here, we've got some spring forces and some spring energy. So we're ticking off a big chunk of the equations on this list, and here we go. So the basic thing, let's talk about work. We have a formula that says work is force times distance or displacement. I'm not so sure why physics people switched to D for displacement instead of X for displacement. So you'll see me sometimes write it as F dot X like this. Now, of course, the dot product in here means we're thinking about things in terms of what's parallel to what. So for example, if I've got my cow here and I'm pulling on the rope of the cow this way, if my displacement and my force are in the same direction, then this dot product is not going to really matter. But if I start to pull up or sideways, so if the cow's going this way and my pull is sideways, then I need to take the angle into consideration. So what would that look like? That would mean that my displacement would be going this way and my force would be going this way. And I need to pay attention to the angle between them, which we generally write as phi. And that way my work is going to be the magnitude of the force, the magnitude of the displacement, and the cosine of the angle between them. Or generally what that means is I need to find, if I look at my force vector here, I need to find what component of my force vector is in line with my displacement vector. So if I take my force vector and I break it into components, one component this way, one component that way, it's this component. That component right there is going to be F times the cosine of the angle, if that angle is right there, right? Okay, so that's something to look at. Now, we also talked about power a little bit. Power is going to be the rate of use of work. So power, I should mention that the units up here are joules. Okay. Power is a rate of using work. So power, we're going to have work divided by time, and these units are going to be watts. And I think I pointed this out in class that we've got a W for watts, and we've got a W for work. So just pay attention there. But since this is AP Physics and we like to use calculus, sometimes your rate of work is not going to be constant over time. So instead of having just dividing like this, we can actually turn it into power being dW dt, an instantaneous use of power rather than an average use of power. And that's what we saw over here on the equation sheet was this instantaneous use of power right here, dW dt. Now there's another formula over here for power as well, so let's take a look at that one. We can also have power as force times velocity, like this. So what do we mean by that? If I'm taking my cow and I'm dragging my cow along the paper right here, I'm applying a force to the cow. Let's imagine the cow is just going at a constant speed right here because of friction or air resistance or something. So I'm just pulling the cow at a constant speed like this. I can figure out how much power that takes to pull the cow at a constant speed by taking my force times my velocity and noting that once again it's a dot product. So this is going to turn into F, V, and cosine of the angle between them. So if your force and your velocity are not in the same direction. And one of the homework problems has to do with this as well. So once again, power is force times velocity. If I'm exerting a certain force and making my object go at a certain velocity, then that's going to mean a certain amount of power that's going to be associated with that. So a couple of the other things that we saw over here were some definitions for different types of energy. So I want to talk about kinetic energy and potential energy over here. And these formulas hopefully use something that you've seen before as well. We've got K for kinetic energy. I'll sometimes write it as KE, but physics people just like single letter variables for things. So K is going to be 1/2 mv squared. That's going to be the energy that something has when it's in motion, moving at a certain speed and has a certain mass m. So if my car is moving at a certain speed, I can take 1/2 mv squared and figure out how much energy it has. Excuse me. And then we have U, G for gravity, and that's going to be mgh. That's going to be how much potential energy something has if you're going to raise it up. So if I've got my cow and it's a certain height above the ground, whatever this height is right here, and whatever the mass of my cow is, then that's going to be how much potential energy my cow has as it's being raised up. Okay, so that's some of the basic things, some of the just definitions. So how do we solve problems with this? So let's do sort of an easy problem here. Let's say I'm going to take my cow and I'm going to drag my cow across the floor. Let's make it a frictionless floor for right now, and we're just going to investigate some things that we can do with work and energy and solving some problems here. So let's just draw, just real simple. Here's a free body diagram. There's the cow. Let's make it have the mass of the cow is, I don't know, 500 kilograms or something. I don't really know how much mass a cow has. And I'm going to apply a force on the cow of, say, 20 newtons. And I'm going to apply that force over a distance of, I don't know, let's say 10 meters. My question over here is, how fast is the cow going to be going over here? And let's say that its initial velocity over here is 0. So we can actually solve this using forces. We can use F equals ma and find the acceleration of the cow, and then figure out the velocity over here using some kinematics equations. But we can also use work and energy. The big key aspect of this whole unit is called the work kinetic energy theorem. And then work and kinetic energy theorem says this, just in equation form. The amount of work you do on something is going to be equal to its change in kinetic energy. And now I wrote KE over here instead of just K, so better probably to write it as, work equals change in kinetic energy like this, or final kinetic energy minus initial kinetic energy. So we can use kinetic energy to figure out how fast something's going, and we can figure out the work. So let me just show you the example of this problem over here. I know my work is force times distance. Since my force and my distance are parallel to each other, I don't have to worry about the angle. So I can have my force times my distance. That's going to be equal to my final kinetic energy minus my initial kinetic energy. Of course, that's just 1/2 m times my final velocity squared minus 1/2 times m times my initial velocity squared, which is 0. So now I can pretty easily figure out what my final velocity is over here, plugging in some numbers. I've got 20 newtons times 10 meters for my distance, 1/2 500 kilograms, and then my final velocity squared, and whatever that turns out to be in terms of the numbers, I don't really care. So once again, it's just a different way of thinking about solving problems using energy instead of using forces. And this work kinetic energy theorem is what allows us to say that the work is the change in kinetic energy. So when you do work on something, say the engine of this car is doing work to speed it up, if I can figure out how much energy the engine put into the car, then I can figure out its change in kinetic energy that way. Let's see, another example is just a classic example of just dropping something from a certain height. So let's say I've got my cow up here. I don't know why I'm going to drop the cow, but okay, sorry, Mr. Cow. And let's say, I don't know, something like 15 meters tall, and once again, I've got a mass of 500 kilograms, which isn't actually going to matter. And I want to figure out what's the speed when it hits the ground, my final velocity over here. And we can solve this with kinematics equations pretty easily, but we can also solve it with work. So what's happening is, on the way down, gravity is exerting a force, a gravitational force on the cow, and it's doing work to speed up the cow as it's going down. So I can say work is going to be my change in kinetic energy. That's just a force times the distance over here. And once again, this is my final kinetic energy minus my initial kinetic energy. Force of gravity over here, let's just skip out on numbers for now. That's just going to be mg. And then my height over here, I'm just going to leave as d. So I can write mg as my force. and my height over there is d, and then that's going to be 1/2 m times v final squared, and then I don't have any initial kinetic energy if we start at 0 from up there. And so I can actually cancel out the mass in this one, and I can get something that says my final velocity is square root of mgd, or this might actually be written differently as square root of mgh, or something like that. Now this is a little bit of a clue right here into thinking about conservation of energy, which is really kind of what this work kinetic energy theorem is about. Not quite ready to talk about conservation of energy yet, but we'll get there soon. And it's really just equating a potential energy here to a kinetic energy here. One last thing I wanted to share here, actually two things. We also have springs. So we're going to be getting into a bunch of things with springs. And physics people like to think about springs a bunch. It's just a different way of storing potential energy inside of a spring. So we've got some formulas we'll be working with and kind of deriving in class as well in terms of springs. The ones on the equation sheet over here are these two right here. So that's us. Can you see that? Is that going to focus? Let's see. See if I can get it to focus a little better. There we go. So this is spring force and spring potential energy. For the spring force, what we're talking about is how much force does it take to extend a spring, right? And it actually turns out to be not a constant force. So as I pull further and further and further, the force gets bigger and bigger and bigger to extend the spring. Or really, we're talking about how much force does the spring pull back on me with. And then this formula over here was spring force is minus k times x, which means that the amount of force the spring pulls with is proportional to the distance that you stretch the spring. So the classic thing is if I've got a spring and then I try to extend the spring, so here's the next picture and there's the spring extended, this distance right here is going to be, well, the force that the spring is going to be pulling back with is proportional to this distance right here. This k right here is called the spring constant. Spring constant. Good. And that's really going to tell you how stiff or stretchy the spring is when you're trying to extend the spring. The next formula we had down here was a potential energy stored in a spring. So let's go back now and actually look at what this formula is saying right here. So work and energy are very similar to each other. If I do work on something, then I've added energy to it. And so let's look at what's happening here with this integral, right? So our formula before for work was force times distance. Well, what if your force is changing, varying with the distance? Then what number would I put in for this force right here if I'm trying to find the work that's done by a spring? So whenever you have something that's changing with a variable over here, this is going to turn into an integral. So what we need to change now is, instead of work is force times distance, work is going to be integral of force over a particular amount of distance right here. It's still a dot product, so we still need to consider whether the force and the distance are parallel to each other or not, and deal with that if we need to put in a component. But this lets us figure out the work that's done on a varying force. So in other words, how much work does it take to stretch this spring? Because the force that I'm applying to the spring is changing as I'm stretching it. So I can't use this formula right here because I don't know what to put in for F. Well, F is 0 here, and it's getting bigger and bigger and bigger. So what number do I put in for F if I stretch this thing, a certain amount of centimeters? So it turns into this formula. Now on the equation sheet over here, it uses the variable r instead of x, and r can just mean any vector in any direction. So if I've got a coordinate system here, a three-dimensional coordinate system, and I just have a vector r that's going in any direction, I can figure out the work that's done by a force relative to that particular vector. So that's why it's dr over here, but really it's just almost commonly known as F times dx, unless you're doing something in multiple dimensions, which just makes things a little bit trickier. And notice how these are in bold. So the F and the R are in bold, which means that needs to be a vector and that needs to be a vector. So coming back over here, that needs to be a vector and that needs to be a vector, and that is a dot product. So what we'll figure out in class is if I have this as my formula for work, and then I try to take an integral of it, and just make a little bit of a spoiler here, I guess. If I'm integrating this one up here, there's my spring force. So if I'm integrating minus kx and then dx, right? Then we can see what's going to come out of this thing is going to be 1/2 kx squared. And it's a negative, and we'll deal with the negative as well. Oh, there go my lights. Hold on, I got to turn the lights back on. Okay, good, perfect. So the negative is something we're going to have to kind of deal with as well. It doesn't really show up as a negative in terms of work because work always has to be a positive value. It's not a vector over here. It's really because the force is going one way and the displacement's going the other direction, right? So technically, when I'm pulling on this spring, the spring is pulling that way, but here the spring's pulling this way, but the displacement is this way. So they're in opposite directions to each other. So there really should be a cosine 180 inside of here, which is just going to take out my negative number. So there's our spring energy stuff. I wanted to show you this formula for work as an integral. I wanted to show you this work and energy, the work kinetic energy theorem. These are just a couple of bits and pieces that are important to sort of keep in mind. It's not the jazziest stuff, so that's why I think it's better to just show you in a video rather than take time in class to do it. Okay.